Welcome to this video on thermodynamics. Today, we're going to break down this complex thermodynamics flowchart and understand the key relationships between energy, work, heat, and entropy. Thermodynamics is the branch of physics that deals with heat, work, and temperature and their relation to energy and entropy. This flowchart might look intimidating at first, but we'll go through it step by step to understand how these equations relate to each other. Let's start with the fundamental state functions in thermodynamics. The four main state functions are internal energy, represented by U, enthalpy, represented by H, entropy, represented by S, and Gibbs free energy, represented by G. These are called state functions because they only depend on the current state of the system, not on how the system got there. This is an important concept in thermodynamics. Let's focus on the first law of thermodynamics, which is essentially conservation of energy. The first law states that the change in internal energy of a system equals the heat added to the system plus the work done on the system. Mathematically, we write this as delta U equals Q in plus W on. Here, Q in represents the heat added to the system. When heat flows into the system, Q in is positive, and W on represents the work done on the system. When work is done on the system, W on is positive. It's crucial to understand this sign convention. Heat added to the system and work done on the system both increase the internal energy. Now, let's look at how to calculate work in different thermodynamic processes. For processes that involve volume changes, the work done on the system is given by W on equals negative P times delta V. Here, P is pressure and delta V is the volume change. Notice the negative sign. When the volume increases, the system does work on the surroundings, so the work done on the system is negative. For an isothermal process with an ideal gas, where temperature stays constant, we can use the equation W on equals negative N RT ln of V final over V initial. Let's work through a simple example. If 2 moles of an ideal gas expands isothermally from 10 liters to 20 liters at 300 Kelvin, what's the work done by the gas? Using our equation, we get W on equals negative 2 moles times 8.314 joules per mole Kelvin times 300 Kelvin times natural log of 20 liters divided by 10 liters. Simplifying, we get negative 3,458 joules. The negative sign confirms that work is done by the system, the gas. Now let's move to heat transfer in thermodynamic processes. For an isothermal process with an ideal gas, the heat transfer is given by Q in equals N RT ln of V final over V initial. Notice something interesting. For an isothermal process with a perfect gas, the heat added to the system equals the negative of the work done on the system. Or mathematically, Q in equals negative W on. This makes sense from the first law, delta U equals Q in plus W on. In an isothermal process, the internal energy doesn't change, delta U equals 0, so Q in must equal negative W on. Let's return to our previous example. For the 2 moles of gas expanding isothermally, the heat added must be positive 3,458 joules, exactly offsetting the work done by the gas. Let's now explore entropy, a concept that often confuses students. Entropy is a measure of the disorder or randomness in a system. For a reversible process, the change in entropy is defined as delta S equals Q reversible divided by T. Here, Q reversible is the heat transferred in a reversible process, and T is the absolute temperature. For an isothermal process with an ideal gas, the entropy change is given by delta S equals N R ln of V final over V initial. For our expansion example, let's calculate the entropy change. Delta S equals 2 moles times 8.314 joules per mole Kelvin times natural log of 2, which gives us approximately 11.5 joules per Kelvin. This positive value makes sense. As the gas expands, it becomes more disordered, increasing its entropy. Next, let's discuss enthalpy and Gibbs free energy, 2 more important state functions. Enthalpy, H, is defined as H equals U plus PV. The change in enthalpy is delta H equals delta U plus P delta V. At constant pressure, the heat added to the system equals the change in enthalpy. Q in equals delta H. Gibbs free energy, G, is defined as G equals H minus Ts. The change in Gibbs free energy is delta G equals delta H minus T delta S. Gibbs free energy is particularly important because for spontaneous processes at constant temperature and pressure, delta G is negative. At equilibrium, delta G equals 0. Let's now discuss heat capacities, which appear throughout the flowchart. Heat capacity, C, is defined as C equals Q divided by delta T. There are two important types of heat capacities. C sub V, heat capacity at constant volume. C sub V equals delta U divided by delta T. C sub P, heat capacity at constant pressure. C sub P equals delta H divided by delta T. For ideal gases, the molar heat capacities are related by C sub P, M equals C sub V, M plus R. We can also define specific heat capacity, C sub S, which is heat capacity per unit mass. C sub S equals C divided by M. And molar heat capacity, C sub M, which is heat capacity per mole. C sub M equals C divided by N. Now that we've covered the key components of the thermodynamics flowchart, let's see how they all connect together. In the flowchart, equations are connected by red arrows labeled sub, which indicate substitution of one equation into another. Green arrows, which show logical progression or derivation. Purple arrows, labeled integrate, which show integration or conversion between different forms. And brown arrows, which indicate special cases, such as constant pressure or constant volume. For example, if we want to find the work done in an isothermal expansion, we'd use the ideal gas law, PV equals nRT, together with our work formula, W1 equals negative P delta V. To derive W1 equals negative N, our TLN of V final over V initial. To summarize what we've learned, we've explored the key state functions in thermodynamics: internal energy, enthalpy, entropy, and Gibbs free energy. We've seen how the first law of thermodynamics relates changes in internal energy to heat and work. We've learned how to calculate work in different thermodynamic processes, especially for isothermal expansions and compressions of ideal gases. We've understood how entropy changes in various processes and its relationship to heat transfer. We've covered heat capacities and their relationships for different processes. Finally, we've learned how to navigate the thermodynamics flow chart to solve complex problems by following the connection paths. Thank you for watching this video on thermodynamics. Understanding these relationships takes practice, so try working through example problems to solidify your knowledge.